Okay, welcome back everyone. I hope you had a nice lunch and poster session. So we're going to start with the three talks of the afternoon. The first one is Pablo Parrilo from MIT. He's going to tell us about chordal structure in polynomial networks. Pablo.
Okay, great. Thanks for the introduction and thanks for the invitation. I guess it's a pleasure to be here today. So let me tell you what this talk is about, which is really trying to understand how to exploit a certain kind of structure for solving systems of equations. And everything that I'll say is joint work with my former student, Diego. So Diego is now again at MIT, like in the math department as an instructor. So what's the background or what's the problem that we're really trying to understand? How to solve systems of polynomial equations in many variables in some efficient way. Right, so the idea is that, I guess I don't need to motivate this a lot. There's many applications where one would like to do is to solve a large system of polynomial equations, including applications, for instance, that come from robotics or from power systems or from chemical equations. These are essentially some mass action kinetic equations. And the feature, perhaps, that I want to emphasize on the particular systems of equations that appear in many of these applications is that they're not arbitrary. Right? That typically, when you look at the equations that appear in each one of these problems, the equations don't involve all my variables at the same time, but every single equation typically involves a relatively small subset of variables. Right? Of course, a whole system connects all the variables together, but typically when you look at the equations, each equation connects a relatively small subset of equations, or perhaps not that small. And somehow this is a very interesting feature, and somehow exploiting this in the context of nonlinear equations is actually quite non-trivial. And this is what I'll try to explain a little bit how things work. So what's a mathematical setup? Again, I only have a few equations to describe this, but the basic idea is that if we're trying to solve a system of equations in here in n variables, and I have m of these equations, and I guess we start with variables from 0, we're C people, I guess. And what we're going to do is we're going to abstract. I'm going to throw away essentially all the structure of my equations, and the only thing that I'm going to try to retain from this is which variables are talking to each other. Right? So what I'm going to do is essentially construct from my system of equations a graph abstraction. So I'm going to construct a graph. This is usually called the primal graph or the Geifman graph if you're a constraint satisfaction person, where the nodes are variables. So I'll give an example in just a second, but the nodes are going to be my variables. And I'm going to go through my equations, and for every equation, I'm going to draw a click connecting the variables that appear in that equation. Right? So here's a simple example. I have this system of 4 equations. So it's this equal to 0, this equal to 0, this equal to 0, and this equal to 0. So I have 4 variables that are appearing in here, 0, 1, 2, and 3. So these are my nodes in here. And I'm going to go through each one of the equations. I'm going to draw a click connecting the variables that appear in each one of the equations. So for instance, my first equation contains variables 0, 1, or 2. So I'll draw a click, that nice triangle over there. The second equation contains only variables 1 and 2, so I'm going to draw again an edge in there, and the same thing for all the other ones. And I'm going to ignore pretty much all the other information about what the coefficients are, what the specific equations are. So I've thrown away lots of information, and I obtain this graph. Right? And the question is, does the structure of this graph tell me anything? If it does, about how easy or how hard is to solve this system of equations. Right, so if you want formally, what we've done is we abstracted this polynomial system into a graph, in this case. If you're a fancy person, you can do hypergraphs. If you're an even fancier person, you can construct a system of polytopes that connects these things. I'm not fancy today, I just want to do a graph in there. And the natural questions that I think one wants to try to understand is, does this graph structure help you at all to solve the system? Right, is it the case that this graph is simple in some sense, that solving my equations is going to be simple in some sense? Right? And again, depending on who you are, solve may mean very different things. If you're a numerical person, then solve may mean I want to obtain 6 digits of any root of my system. If you're an algebraic person, you may need, I want a full description of the idea, like on a Grobner basis. There's all kinds of intermediate notions in there of what does it mean to solve a system of equations. And this is kind of important because typically many systems have exponentially many solutions. So you cannot even think about writing down all the possible solutions of your system, right? But in particular, what they're kind of interested in is are there ways of somehow preserving the natural sparsity structure of the systems in here? Because typically you may have equations with thousands of variables. Perhaps your equations are relatively simple. They don't connect all the variables together. And we would like to preserve this sparsity. And perhaps the analogy that I want to have in mind is think about when you solve sparse systems of linear equations. When you solve AX equals to B and A is sparse, you don't want to solve things in a way that you get filled in. Right, good. So this idea of going from somehow some object into a graph typically is called graphical or hypergraphical model. It has appeared in many, many areas in many, many different forms. Depending on who you are, again, you may have seen some of the things in numerical linear algebra against sparse matrices, probabilistic graphical models, there's a beautiful area called constraint satisfaction in computer science, database theory. I mean, they're all kind of slightly different forms of some meta-theory, which I'll describe in just a second. There's a lot of names associated to this, again, depending on which community you're coming from. But really what's kind of interesting, and this is what I'll spend at least the first 10 minutes describing, is that there's two key notions. In here, one is the notion of chordality, and the other one is the notion of treewidth. And I'm going to try to explain why those somehow unify all this stuff, and somehow they're very natural and very useful notions in there to understand how this goes. What's kind of interesting, or what was kind of interesting for us, is that there was really not any work that at least we could see in terms of how do you exploit this when you're actually solving polynomial equations, right? There was, of course, in the linear case, there were some things. In the finite situation, there were some other cases. But if you actually want to solve polynomials, things are tricky. And one of the things I want to highlight is a little bit things that explain a little bit why in the polynomial case, things are a little bit more complicated than in the general case, and how things appear. And of course, in the optimization side, one can think about either the discrete situation or the continuous situation. The continuous situation, lots of the kind of things that we're talking about in here will appear in a quite natural way, particularly if you want to solve minimizing functions with polynomial cost functions. Good. So I have these two words that I have in there, and as I said, I'm going to spend the next 5 or 10 minutes explaining exactly what this chordality business and treewidth actually is. So some of you may know the definition of sorry, I keep going back and forth. Some of you may know the standard definition of chordality in terms of the cycles of a graph and whatever. Let me present an equivalent definition which is actually much more matched to the kind of elimination things that we want to try to do. Don't parse the definition for a second, stay with me, and I'll try to explain what the basic idea is. So it's a property of a graph, right? It's a property about the graph being chordal or not being chordal. Now, what is the idea about chordality? Let me define a notion first, which is a notion of a graph having what's called a perfect elimination ordering. So what is a perfect elimination ordering? Let me illustrate this with an example that I like, which is very simple, which is imagine that you have a party, all the people in the party are actually nodes of your graph. Right, and the edges are whether people are friends or not with each other. So what is a perfect elimination ordering? We're going to say that if there's a perfect elimination ordering, if there's a way for people to leave the party in such a way that some nice property happens. So what happens when you leave a party? If you're a well-educated person, you gather all your friends and you say bye to each other, right? So what you want to have is a property that when you leave the party, all your friends are actually friends of each other. Right? So if there's a way for people to start leaving a party one by one in such a way that when they gather all their friends and say bye, all their friends are already friends with each other, then we're going to say that your graph has a perfect elimination ordering. If you want to make it mathematical, it's exactly this property. There has to be some ordering of the nodes in such a way that when you look at the induced clique or the induced subgraph, by looking at the remaining edges in there, they have to form a clique. Right? It's a very simple property. Nice example, I really want to make sure that you understand it. So for instance, for these two graphs, one of them has this property and the other one doesn't, right? So for instance, it's pretty clear to see that this graph has a perfect elimination ordering, because I can number them like 1, 2, 3, and 4, and this property will be true, right? When this one leaves, the friends are friends of each other, and I keep going, but this one does not. Right? So it's a nice property to have. What's a chordal graph? It's a graph that has a perfect elimination ordering. So this graph in here is a nice chordal graph. This graph is not. Right? Nice definition. Again, there's a lot about many other equivalent definitions. But what this tells us in particular, that these are things that are very amenable to elimination. Right? Somehow when you eliminate things, when you get rid of things, the structure is somehow preserved. No new edges are created, if you want. And if you know anything about numerical linear algebra, if you ever played with MATLAB and had this Cholesky factorization of sparse matrix, this is exactly what you do when you compute the ordering in such a way that the sparsity pattern of the Cholesky factor remains the same, that you don't have fill-in. Right? So if you have a random matrix, and you do a Cholesky factor with respect to some random order, you get some horrible thing with a lot of fill-in. If you're smart and order things in the right way, then things become a lot nicer. Right? It's, again, goes back to the 60s. It's all kind of well known. Now, what do we do? So remember, this is chordal. This is not chordal. So what do you do when you have a graph which is not chordal? You just add edges until you make it chordal. Right? So for instance, in this case, of course, I can just add this edge in here, and I'll make it chordal. In fact, I can also add this one, and it'll be chordal. So the idea is that I would like to add edges until I make it chordal, but not add too much. Right? And that's exactly this notion of a chordal completion. So what is a chordal completion? It's a graph with the same vertex set that contains all the edges of G. It's a superset of G that is chordal. And what is treewidth, the other thing that I wanted to define, is exactly the size of the largest clique of the smallest chordal completion. So essentially, I try to make my graph chordal by adding the smallest number of edges, if you want. It's not exactly that, but it's what they say there. So, okay, these are definitions. They're not easy to parse in real time. I don't care if you get all the details about this or not. But what I do care is just to get what's the operational meaning of chordality and why it's so important. So chordality is really a graph parameter, or treewidth, if you want, is a graph parameter. It's a number that you can ask to any graph, what is your treewidth, and your graph will tell you my treewidth is 15, whatever it is. And it measures how close your graph is in the spectrum from being a tree to being the complete graph. So if your treewidth is 1, then your graph is a tree or a forest. Right? If the treewidth is 2, it's a very nice family called series parallel graphs. And if your treewidth is 10, then it will be exactly the complete graph.
What's number 2 called?
Series parallel graphs. Yeah, series parallel. Series. Yeah. So the graphs that you can arrange, by, yeah. Good. So why people care about this? And again, if I were to, horrible thing, I'm going to summarize 40 years of research in one sentence. And that's really that if you're trying to solve an NP-hard problem, pretty much any NP-hard problem with some disclaimers on graphs of small treewidth, then things become hard. So easy. Easy. Right? So if I try to solve max cut, if I try to solve coloring, if I try to solve whatever on graphs that live over here, up to some constant treewidth, then there's actually polynomial time algorithms, in fact, linear time algorithms that will do this, exponential in the treewidth. Right? So the first time that you hear this is kind of a miracle. It looks really weird. Let me just give an example, a very simple example of why something like this could even be possibly true, which is a case, for instance, of doing stable set independent set on trees. Right? So what happens in this case, we all know, I guess, or it's an optimization meeting, I guess, so many of you know about the stable set or independent set problem. Right? What I'm trying to do is to find a subset of nodes, the largest subset as possible, in such a way that node to nodes are neighbors of each other. So for general graphs is, of course, NP complete. And I claim, An application of what I just said is that in particular in the case of trees, for instance, this is linear time solvable. Right? And in fact, it's not that complicated. What's a key word, if you want, that should come in your mind to do this, is really dynamic programming. Instead of doing dynamic programming on a linear structure like the way that we think of the classical dynamic programming like in Bertseca's book or whatever, you really dynamic programming on a tree from the leaves all the way to some root node. And essentially you can write some kind of recursion. I don't have time in here to explain in detail. It's a very simple recursion. Any of you will come up with this in 30 seconds. And essentially this will actually solve the stable set problem on trees. For graphs of constant tree width, it's a little bit more complicated, but not much more. And you'll get something that's very much of the same form. Right, so again, details are not crucial for this talk. What is important if you want is this picture. That quite often when you're trying to solve problems on graphs, and your graphs have small tree width, then quite likely there's nice algorithms to do this. Sorry? You need? Yeah, but all that, you compute in polynomial time from this and this. Sorry?
Is there any example where this is not that you are aware of?
So I'll talk about this in just a second. Yeah, so if I write, I started the talk with I'll go from a polynomial system to a graph, and now I tell you somehow if the graph is simple, some meta-theorem tells me that things should be good, and this is how we started this. We thought, oh, great. Then essentially that means that if the graph is simple, I can solve my system of equations. Right? But life is not that nice. Pretty much a second thing that you would think is, okay, let me go back to subset sum. Perhaps the simplest problem that you can possibly think about. So what is subset sum? I have a set of integers, and I'm trying to find a subset of these integers that add up to 0. Right? It's kind of pretty easy to see that you can write a system of polynomial equations. These are the one in here in variables s sub I. Somehow the s sub i's, think of them as the partial sums of this set. But this is really just a system of polynomial equations. If you draw the graph associated to the system of equations, the graph that I talked about at the beginning, what you'll have is a beautiful path in here, because each equation only relates two consecutive variables in there. So of course, a path is a tree. A tree has tree width 1, but this problem is NP-hard. So somehow, my meta-theorem, doesn't quite work, or, there were all kind of disclaimers and asterisks, if you want, in there to actually apply in a situation like this. Right, so the polynomial situation is more complicated, than perhaps the cases that we talked about before, and one of the things that I want to focus in here is just to give the intuition of why this is true. So, yeah, but I could pick other problems and the same thing would be true. That's not really the issue. Yeah.
That's a quick question. Sorry. So for stable set, if you were to forget the graph, right, it is a system of polynomial equations.
That's a system of polynomial equations, right?
Right. But for your previous example, stable set, if you write the system of equations and then draw the graph,
yeah.
you would have no trigger?
No, a lot depends on which formulation you use. Okay. But yeah. Okay, good. So what's the other second part, perhaps, we should keep in mind why the situation in the polynomial case is different? Because, one of the beautiful things of linear equations, if you do elimination the right way, when you do Gaussian elimination according to a perfect elimination ordering, then the graph structure is preserved and everything is kind of nice and whatever. But if you do somehow the nonlinear analog of that, which is kind of somehow doing Grobner, or the polynomial analog of that, which is doing Grobner basis, then Grobner basis very quickly destroy the chordality or the sparsity structure of the graph. Again, even if you don't know what the Grobner basis is, the idea is if you have a system of equations that may look like this, where the path, where the structure of the graph is very simple, a path just like before, then it so happens, for instance, in this example, that every Grobner basis will somehow contain polynomials that connect x0 and x1. So somehow they will break down immediately the locality property of your system of equations. So what that means, again, the details are perhaps not terribly specific, that somehow we cannot directly extend some of the things that happen in the linear case. So somehow the question, and this motivates this notion of chordal networks that we'll talk about before, that we'll talk about later, whether there's alternative descriptions, somehow even of the solution of a system of equations that will play nicely with the graphical structure. So again, let me at least resolve quickly where this apparent contradiction was coming from. I told you two things that are contradictory. Right, on the one hand, I told you that, I mean, not me, but 40 years of research to tell us that trees are good. On the other hand, the simple example shows you that trees can be NP-hard in here. So what is a difficulty? I mean, what's failing in here? Or what's hidden, if you want, under the rug? So what is the idea of the solution method that I was telling you? Somehow you have to do dynamic programming. Right? And when you do dynamic programming, if you think about it, there's really two things that are going on. On the one hand, you need some kind of nice combinatorial structure, right, that allows you somehow to take an object and propagate it along the graph, or propagate it along time, if you do the value function along time. But also, if you want to do this in a computationally tractable way, you also need a way to ensure that the complexity of the object you're propagating remains bounded. Right, that whenever you take something and you propagate it on your tree or on your time axis or whatever, that this doesn't grow, that this doesn't become a more and more complicated object. And that's exactly what's kind of failing in this case. The nice graphical, the nice combinatorial structure of chordality allows dynamic programming to work in principle. But somehow you need to control the complexity of this object that you're propagating along the P, and without this, you'll run into trouble. And this is not, in a sense, a new phenomenon. If you're a controls person, you've seen this, when you try to solve any problem using dynamic programming, right? Except in very nice situations, like a linear quadratic case, that the value function remains quadratic. If you try to do this in the nonlinear, even the polynomial case, the value function becomes more and more complicated as you pass it along. If you do statistical inference, nonlinear filtering, exactly the same thing is true. It's kind of a general phenomenon, but in here, I think it becomes quite transparent what it is. So how does one get around this? Essentially, you need to impose conditions on the geometry. I will not tell you the details. I'll just give you a cartoon of what's actually happening and what we want to do. But in this algebraic setting that we're doing, you're really thinking about polynomials and varieties and solution sets, whatever, there is a very natural condition, or there's a very natural way of thinking about how to control this geometry, which is in terms of understanding the degree of the projections of the solution set into some particular subspaces. Again, this is just a cartoon. So what is this cartoon in here? This thing in red in there is the variety, which is a solution set. Think about these are all the solutions of my polynomial system. Now, what do I have in here? These are these three hyperplanes, if you want. They're the spans of the subsets of they're the subspaces spanned by the maximal clicks of my graph. So for instance, remember before my subspace in here was 0, my graph was 0, 1, 2, and 3. The maximal clicks in here, they're the span of 2 and 3. That's this thing over here. And in here I have the span of x0, x1, and x2. So that's it, so this subspace over here. So what do we need? This object may be really, really complicated. May have exponential many points, the degree may be extremely large, may be awful to describe. But what I need is that the projections on these subspaces, on these small subspaces, because my largest clicks are going to be small, I need these ones to be controllable. And controllable or nice in the algebraic setting really means that these are low degree varieties of low degree. Now, again, it looks like a weird condition. It's very natural from the algebraic geometric viewpoint. But in particular, this explains in a very nice way why, for instance, in the previous case, in the 0-1 situation, or in the finite situation, these conditions are automatically satisfied. Because what do you have in the discrete case? This variety is just an arbitrary subset of the hypercube. I have a hypercube, the corners of the hypercube in dimension 1,000,000, whatever it is, and I have some arbitrary subset in there. And now I'm projecting this into a small hyperplane, into a small subspace, into only k variables. And even though you may have 1,000,000 points up there, when you project it on 3 variables, all these points are actually going to lie on top of each other, and at most, you're going to have 8 points. Right? If I only look at the values of x1, x2, and x3, Even if I have, my space is million dimensional or whatever, I'll only see 8 points. And what you really need to do is some way of gluing all these things together, and it turns out that under some conditions, one can glue all these projections in a nice way and recompose things. What's kind of interesting is that this not only works in the finite case, but also works in some other cases of nice geometry, like most of these determinantal varieties, which I will not say too much about this. So again, this is a basic picture. If you want to see the details, there's a couple of papers. Actually, they're already published. These are the preprints, where we solve these kind of things into a couple of different ways. Some algorithm based on some kind of elimination procedure, some other algorithm, some other method based on something called Chordal networks. And this is really what I want to spend the rest of the time talking about. Because it's a very interesting way that the starting point of this is actually this Chordal structure. But actually what we ended up with is like a very flexible and a very nice way of representing the solutions of equations in a way that I'll make it more precise. But this can be really interpreted, on the one hand, as a generalization of something called BDDs, if you know what BDDs are, binary decision diagrams. But also it's a very nice data structure that allows me to take a polynomial system and compile it into some intermediate representation that I can then query in order to do different kinds of tasks. And this is what I'll try to explain in the next few minutes. So what's the starting point? Again, it's a particular example. We don't care about this particular example. We could solve this particular example in many other ways. But I think this illustrates a lot, I think quite cleanly, the kind of problems that one runs when solving polynomial systems. So let's start with a graph, in this particular, this simple cycle. And let me try to understand, for instance, let me write a system of polynomials that encodes, for instance, in this case, the colorings of a graph, the 3 colorings of this graph. It's not very difficult to see that you can write a system of equations that are in one-to-one bijection, whose solutions are in one-to-one bijection with all the colorings of the graph. The idea is that what you can do is color each node with a root of unity. Right? I write the equation x sub I cubed minus 1 equal to 0. That says I have to assign a cube root of unity to every root, and then I have compatibility conditions for every edge that says that I have to assign different colors. So the point is, I can compute, if I solve these equations, I essentially get all the colorings of my graph. In particular, I can detect if it's 3-colorable or not by solving these equations. Now, I want to make the contrast between how easy any of us would find coloring this graph with 3 colors. I think any of us or our children, whatever, could color this with 3 colors. But on the other hand, if you feed this to any somehow computer algebra software or whatever, then you may ask to compute the Grobner basis or something. It will give you 13 huge polynomials, like for instance in here. So you'll be completely unable to understand that somehow this system is actually very, very easy to fully understand what's happening in there. Yeah, that's for this example. And if you try to do it without 15, this will never finish.
Is it easy to see why that encodes the coloring?
So the first equation, and the second one says when you have 2 adjacent nodes, one for every edge, then the ith root and the jth root, they have to be different. This is essentially x sub I, x sub j cubed. Yeah, there's a different way of writing this. It's x sub I minus x sub j cubed divided by x sub I minus x sub j. That's really what it is. And it's a polynomial, and it ends up being exactly this. Okay, good. So I claim that, as I said, that any of us could actually solve this. And in fact, there's a different representation somehow of all the set of solutions of this graph that actually encodes, or of this system that actually encodes exactly what it is. So what's the idea in here? I write some kind of complicated looking, directed graph. So what I have in here is a particular directed graph. In here I have nodes, these nodes in blue that contain polynomials. But the key feature, the details again are not very important for today. But what I wanted to focus is on kind of the following. That somehow the structure of this system is such that if you follow any directed path in here, what you obtain is a triangular system. Triangular system means that I can start at the bottom, solve this equation for x8, then solve the previous equation for x7, then solve the previous equation for x6, and go like this all the way at the beginning. So what this is doing is really writing the set of all solutions as a union over paths of a combinatorial structure, right? And what's kind of interesting in here is that my combinatorial structure is compact, right? This is not too big a thing, but the set of paths is exponentially big. In particular, the set of colorings of the cycle is a Fibonacci number, whatever, this grows exponentially. So, kind of very easily we can produce examples, kind of where there's just not enough solutions. There's not enough ways of representing all the solutions other than in some kind of implicit representation. Right, and this is really the point that I want to emphasize. What we're doing in here is we're writing a data structure. This data structure I can then query. For instance, if you ask me produce a solution, then I just pick a path. In here, I back solve, and I get the equation that I want, the solution that I want. And this actually includes all of it. Good. So what is a chordal network? Again, this is perhaps the first example that you've seen. What is a chordal network in here? What do they look like? They look essentially like an enlarged elimination tree, kind of, which I'll describe very briefly a few examples later, where the nodes are polynomial sets, just like in here. And it provides an efficient encoding or components of all the solutions in terms of paths and subtrees. How can you compute them? We have an algorithm. I'm not going to this. I'll give you a picture if you want of how the algorithm works. But essentially what you do is kind of some kind of iterations until you refine a description until it becomes stationary, very much like we would do a Grosvenor basis. And what's kind of interesting again, and this is really the key, is that many polynomial systems, they actually admit small chordal networks, even though the number of components may be exponentially large. This is always going to be the case if my system has small tree width, but there are lots of other cases where you don't have small tree width, but you have small chordal networks. And this is something that we don't fully understand yet. So what are they good for? Essentially, once you have a chordal network, then pretty much anything that you would like to do with a polynomial system, you can do it on the chordal network, and you're going to be able to do it efficiently. You're actually going to be doing it essentially in linear time. You can decide feasibility, you can count the number of solutions, that's counting paths on a directed graph, which you can do very efficiently. We can compute the dimension, elimination, radical membership, all the kind of things that one would like to do. One can do much more efficiently. I'll give some examples near the end. So again, I'll just flash a few slides, I think trying to perhaps give you a more complicated example that we have in there. So think about, for instance, now we're trying to understand again in the context of coloring. It doesn't have to be for coloring. So if you have a graph in here, you can compute the chordal completion. Once you have a completion, there's something called the elimination tree, which is exactly this tree that connects, when nodes are leaving the party, they will connect to the last friend, that's still in the party, some kind of nice tree over there. So keep this tree in mind. So what is a chordal network? I'll talk about the definition roughly in a second. But this is, if you want, the impression that I wanted to get of what a chordal network looks like. It has a structure of the elimination tree. This is what the elimination tree looks like. And this is essentially an enlargement of the elimination tree, where now I have polynomial systems in here associated to every node. And just like in the simpler case before, you can take any directed path in here, and what you'll get is a triangular system that then you can start solving backwards. And this parameterizes all the solutions of my system in there, because you can take any path, and this will give you exactly a solution. Right. By the way, I guess I should mention, we have software that computes this. It's actually integrated now with one of the best softwares for computational algebraic geometry, something called Macaulay 2, if you know what that is. So it's actually, I think, a quite nice way of using of implementing these things. So let me perhaps, I will not go through the details, but the algorithm for computing this essentially starts from your system of equations. It constructs an initial chordal network in here, like in this case, and then you apply a series of operations essentially operations like triangulation and elimination successively until you get somehow to the final result that you want. Again, the details don't really matter except for the following. We know exactly how many iterations it takes from the initial system until you get your final Chordal network, and all the operations that you do along the way, they only work with a small subset of variables at a time. So even if your full system has 1,000 variables, if your tree width or the size of your in there is 5, then you'll only work with sets of 5 variables at a time. These are going to change. You're going to be changing which variables you use one at a time, but the point is eventually you'll get this nice thing at the end. The formal definition is perhaps a bit, it's not obvious, but there is a nice way of exactly characterizing what the things are. As I said, I really want to focus on the operational meaning of these kind of things. Why do we care about this? As I said, because once you've compiled your polynomial system into this network, pretty much everything that you would like to do from the point of view of understanding the solution set, you can do it efficiently. If you want to compute, for instance, the components of the variety of different dimensions, you can, there's algorithms for do this. If you want to understand whether something is in the radical or not, you can do this. If you want to count solutions, essentially all the kind of things that one would like to do, once you have a network, you can do it in a nice way. So, of course, things don't come, actually, it's kind of interesting because we didn't start with this, but in the end, I think we realized that this reduces, in the very particular case, to something called, so in the 0-1 case, there's a beautiful object called BDDs, binary decision diagrams. I don't know how many of you know this, but the idea is that something quite similar happens when you try to represent a Boolean function. Right? So if you have a Boolean function of many, many variables, typically this is a huge object, and it's kind of not obvious at all what are compact ways of representing this. If you write the full truth table, this is exponentially big. Formulas, even for very simple functions, sometimes the smallest formula is terribly big or whatever. But there's a very nice representation, something called these BDDs, which is essentially some kind of read-once program, if you want. Essentially, I go through my variables one at a time. I read the value, and based on its value, I branch or not branch, and until eventually I get to the value of my variable. And somehow, many of the same features of that happens in the Chordal case, I guess they specialize. When you look at ideals, monomial ideals, actually, it reduces exactly to the case of BDDs. But in the general case, is of course more powerful. There's a lot of things that we can do. So as I said, we implemented this in Sage and now in Macaulay too, and we applied it to a number of problems in a variety of areas. I will not bore you with a lot of comparison. I need to finish in 2 minutes, and I will. So I will just show one example, which is actually pretty representative. This comes from something called vector addition systems, or reachability problems in lattices, if you want. Where the idea in here, let me not explain too much where this comes from. This is really a problem in algebraic statistics, where one wants to verify these particular polynomials in the ideal generated by these equations. Again, details are not really important. The only thing that I want to focus on, I don't care about the numbers, is that we compared our method, this method with essentially state-of-the-art techniques in computational algebraic geometry, the best methods that can either solve general equations or equations that have this kind of binomial structure in here. And the point is, that, again, the details don't even matter. Our method is Chordal net. The other methods are singular and epsilon. And the point is, even in here, you can directly see the difference between something that scales exponentially with the number of variables in here. So, both of these methods, because they cannot exploit the graphical structure. In here, even though, singular is very clever, it gets stuck around, 30 variables. This is no longer doable in there. Epsilon, again, it knows about the binomial structure, so they can do something better, but again, pretty quickly runs out of steam in there, because again, it doesn't know about the graphical structure. But this Chordal network stuff, it just scales linearly with the number of variables. Right? And these are big, complicated systems that, I think unless somehow, you understand the structure, these are difficult to solve. So somehow the bottom line, which I guess is something that we do know quite a bit in optimization, like, exploiting structure is of course key in terms of obtaining good algorithms. And what's kind of interesting in here is that this very interesting combination of, like, a combinatorial structure and some kind of algebraic things in there. Okay, so this is pretty much my last slide, right on time. Hypergraphical or graphical structure in there may simplify quite a bit, actually, polynomial optimization or polynomial system solving. I'm quite excited, or we're quite excited, Diego, about this kind of notion of chordal networks. As I said, even though we can guarantee that they work in the low treewidth case, there's a lot of other cases where they work even if treewidth is not null. What we really need is that, there is some network of small size, and this is very much like what happens in the BDD case. Right? There's a lot of functions that we know that they have small BDD representations, but somehow it's a little bit unclear why. And I think it's kind of quite intriguing, I think, to what extent this kind of clever encoding of a problem in terms of the paths of substructures of some combinatorial object, they can be extended. If you want to know more, these are some of the papers, and thank you for your attention.
Questions for Pablo? Yes, we can.
So the fact that the complexity of the value function does not grow was only taken into account when constructing the Chordal graph?
No.
Where was that implemented?
So essentially, perhaps let me make that clear, for instance, of why that explains, I guess I left it as an exercise for the reader, but why what I said actually explains why things don't work in here. Right? Because what's actually interesting in here, of course, I can try to start doing eliminating variables at a time in this case, but one of the things that will happen is that when you look at the set of solutions, when you start eliminating variables in here, then the set of equations that you will obtain is actually going to start growing exponentially. So what you need to ensure is whenever you eliminate one of the variables, then you can describe the remaining set in terms of a compact system of equations, which geometrically means exactly that the projection is definable in small degree. So in here we have conditions. Essentially, I didn't mention this in there, but we put some conditions on the polynomial system that are verifiable a priori that will ensure that these kind of things are. They depend, yeah, exactly. So for instance, again, one case is a determinantal case, one case is this finite case, but there's something we define called monomial dominated things, for, yeah. Oh, I should repeat the question.
I need to allow it. Let me get somebody else's question. Aida.
Yep. So in general, so the question is what happens when the graph is not chordal? So when the graph is not chordal, typically what we want to do is to find a good chordal completion. Finding the best chordal completion is hard. It's a well-known problem that has been analyzed, but there's a lot of really good heuristics. For giving a problem, you essentially add a small set of nodes, a small set of edges that will make it chordal. And in a sense, for us, that's not the, that's not the essential. I think the cost of that part is relatively small compared to all the other things that you do. But also in many of the problems that we have, the structure of the graph, because this comes from applications, we immediately know either what is a chordal completion or what is a structure, like problems from grids, that appears a lot. About what? Yes. So, essentially, the only, in that case, the completions tells you that you only need to worry about understanding the geometry on the projections on the subspaces spanned by the maximal clicks. Yeah. And this is, by the way, very compatible with what one does in semi-definite programming, right? All this stuff about semi-definite programming in the chordal case,
Questions? Yes, go ahead. So you would run, so in here we don't do anything specific about the real case.
right? Because one of the things that the real case is much more complicated is that these projections may not even be definable. I mean, there's more subtle things in the real case. Let me say this, that somehow this doesn't appear. I mean, a little bit of these tools do help in that case, because for instance, what this tells you within certain bounds is how you should eliminate variables. What is the right order to eliminate variables. But one of the things is that we know that cylindrical algebraic decomposition is not actually a very good method because it eliminates variables one at a time. But what you really need to do is to eliminate blocks of variables at a time. Because if you do cylindrical algebraic decomposition, you pay a doubly exponential price that it should be only single exponential. And this is true even in the polyhedral case. That's why Fourier-Motzkin is a horrible method, but there's other things that are actually much better.
Okay, one last question. Go ahead.
So, I was wondering if there is like an approximation method version. It's like people run Gaussian-based propagation, even if it is close to this dynamic.
Yeah, so the question is whether there's an approximation version of this. I think it's an excellent question. I don't quite know. I mean, there's a lot of things that can be subtle about it. I should mention, I mean, there's some nice work of Winstock, where they look at the integer programming case. And they have some kind of nice approximation results for integer programming under small treewidth, case. And, but I think you're talking more about something that doesn't necessarily have small treewidth and how you would approximate.
Okay, you get one question. You can follow up later. Okay, sorry, Pablo, let's end it here and come back for Ben Reck's talk in maybe 6 minutes. Okay, or 8 minutes. Thank you.